let's just compute it real quick because I've got this sitting right here. We go 0 to 1, we go x to 1, and we're doing x squared plus 3y squared. Oh, because I accidentally deleted that. Ah, no, I messed up. Yeah, let me try something. There we go. There. .833. Sorry about all this crap up here. So there it is. That integral should yield 0.833, which is the volume that we're looking for. Now, visually, just so you can see what I could not draw for you very well. I believe I have the computer do this for me. Well, that's moving fast. Whoa, what's up with that? That picture don't look right, does it? Did I read the problem wrong? X equals 0, y equals 1. It's almost like my picture got flipped. Interesting. I think I just drew it wrong over here, but it's pretty much the same thing, but this should be turned over, right? This should be turned, rotated. And let's just take a look at it. So there's our bowl. There's our bowl. There was our bowl. And here's the xy plane. This is the bottom. That's x is 0. Okay, so x is 0 is there. This is z is 0. This is, I think, y equals x. And what the heck is this? Oh, y equals 1. Right? That's y equals 1. But yeah, it's the region bounded by all of those, right? You can't see it. You can't see it. So there's the region in there. And I'm going to take everything out of here so you can just see the region that we found the volume of. And it's that piece right there. Can you all kind of make sense out of that picture? It's below the bowl, but above the xy plane, but over that triangular region, this one right here, turned. Got it? All right. Let's look at the next problem. So this is from the book also. I'll turn the light back on. This is number 28 from the book. So same instructions. Find the volume of the solid that's bounded by the following curves. So we have y squared plus z squared equals 4, which now, oh, where'd Milton go? This is your cylinder. This is your cylinder. This is what a cylinder looks like. It's like a circle, right? But you have a free variable here. The free variable here is x, so you have circles that go down the x-axis. So there's your cylinder. So it's bounded by that. It's bounded by x equals 2y, which is a plane, x equals 0, and z equals 0. And they also tell you you're in the first octant. So let me try and show this to you before we actually go figure it all out. There's your cylinder. Here's the YZ plane. So this is x is 0. Right? So we're cutting it there. This is z is 0. That's the ground. Then we have x equals 2y, which is this plane, which is that plane right there, okay? So it's got to be bounded by all of those and be in the first octant. So remember the octants? They started like, here's first octant, second octant, third octant, fourth, and then fifth was on the bottom, sixth, seventh, eighth. That was the first day of class. So we have 8 octants in three-dimensional space. So we are talking about the solid right there. I hope you could see that that's where it was going to be. And then we can take everything out of here. And we are trying to find the volume of this right here. All right? So what we do again is we go into two-dimensional space. This one I think is correct. We draw as much as we can here. So x is 0 is this, right? So got that. X equals 2y. That's this one right here. This is the one that's the trickiest one. That piece right there. Where does that come from? That comes from the cylinder. Check out the cylinder. What you're doing is you're saying, where does that cylinder come down and hit the xy plane, right? That means when does this thing hit the xy plane means when is z 0? What happens when z is 0? If z is 0, you get y is plus or minus 2. So this is y is 2. And then negative 2 is on the other side. So that's this edge right here. Do y'all see that? That's that edge where the cylinder comes and hits the xy plane. Then there's another edge on the back side, which is back here, but we're not going to consider that because we're supposed to be in the first octant, right? We were told to be in the first octant, and if y is negative, then you're no longer in the first octant. So this is our D. And what type region is D? It's both, right? But I'm going to stick with type 1. X is between what? 0 and 0 and what?
4.
Yeah, we have to figure out where those hit. So you'd want to know when 2 equals this line. So y equals 2. You plug it in here. If y is 2, x is 4. So you're able to get that this is 4. So you know the x goes between 0 and 4. And then what about your y coordinate? It's between, this would be 2, right? That's this top piece, right? Y is 2's top. The bottom is this. This came from that. Solve it for y. Y is a half x. Just divide both sides by 2. And then you have to do the top surface minus the bottom surface. The top surface is what? Ooh, this is going to be a little bit different. What's our top surface? The cylinder, right? The cylinder, but solved for what here? You have to solve it for z so that you have it as a function of x and y. So we take this. This will give us our top surface. As a function of x and y, solve for z, you get square root of 4 minus x, sorry, not x squared, y squared. And why am I not looking at the negative? Because I'm in the first octant, right? I'm on the top. So it has to be that top surface. And then what's the bottom surface? Yeah, it's the plane, the ground, right? Z equals 0. The challenge for you is to read the problem and be able to come up with the picture and get all these limits of integration correct, right? That's the challenge. Once you get it all, then setting up the integral, doing the double integral isn't really the point of concern, for me at least. So it's going to be this. That would be your double integral. Top surface minus bottom surface is here. Restrictions on y, restrictions on x. And are you okay doing that? How?
You have to use the trig.
There's trig substitution, right? But your formula sheet actually does have, I believe, in your formula sheet, there is a formula for a squared minus u squared du. Like, there is a formula for that. But you should be comfortable doing trig sub. I know you'd have to roll it back, go back to Cal 2 and remember how to do that, but
wait, why would you do trig sub?
because it looks like there was 3 forms. You could get like constant squared minus variable squared, or you could have constant squared plus variable squared. Excuse me. Variable on the outside? Not for trigonometric substitution. I'm sorry? Yeah, like the Pythagorean identity has to be in there somewhere. All right, that okay? All right, we are done there. Pardon?
Oh, no, yeah, he was asking me about the trig thing.
Trig substitution?
Yeah,
What about it?
If I remember it, and I said, yeah, it's not my favorite.
Oh, yeah. Yeah, trig sub is kind of ugly. But fun, right? I'm pushing it, huh? I'm pushing it. All right, I believe that's it. Yeah, that's it for this section. There's the homework, but you have it already. And we move on. All right. Double integrals in polar coordinates. Let's see if you even know what polar coordinates are. So we've already established the following. We've established that if we're trying to do a double integral over a region, that we can only do double integral over these types of regions. We either have to have a rectangle, which was the easiest one. X is between constants, Y is between constants. Order of integration didn't matter. You could switch it. Everything was great. Then we said, okay, type 1, your x's are between constants, your y's are between 2 functions of x. Or type 2, your y's are between 2 constants and your x's are between 2 functions of y. Those are the 3 things we can handle at this point. We now want to look at some other regions which will force us completely out of our normal coordinate system. Now this coordinate system, do you all know what it's called? Cartesian. This is our Cartesian coordinate system. You know, when I give you an ordered pair, like a number, like parenthesis 2, 4, I mean x is 2, y is 4, right? That's Cartesian. So now we're going to look at a different coordinate system, which is called polar coordinates. And the way we do it is we say, okay, everything you see in red here is Cartesian. If you're sitting here on a plane, on a flat sheet of paper, and you want to get out to this point this point, I can give you an x coordinate and a y coordinate. And that will tell you walk out this distance x and walk up that distance y, right? But I still have to give you 2 things, right? 2 things will get you to that point, the x and the y coordinate. But if you kind of change your perspective on things and draw a right triangle here, then another way to get to that point would be to tell someone standing here at the origin, if they're pointing out the x-axis, just tell them how much to rotate by first. So tell them, hey, turn by 30 degrees. So they're standing there. Let me do it this way. Standing here, I'm pointing down the x-axis. If I wanted to get to my computer, then you either tell me how far to go x, and then how far to go y. That's one way, Cartesian. Or you tell me rotate by 70 degrees, and then walk out a distance of whatever it is, right? And that will get me to that point. But both ways you look at it, Cartesian or this thing called polar, you still have to give me 2 things, right? It's either the x and the y or the theta and the r, how far to walk, right? So they're related to one another. We can just do properties of triangles, of right triangles. The x coordinate is r cosine theta. How do we get that? How do we get that x is r cosine theta? Where does that identity come from? Yeah, just what's cosine theta? I mean, what is cosine theta by definition? Adjacent over hypotenuse, so that's just x over r. And then multiply both sides by r, and you've got an equation for x, right? Same thing here. So once you've established this other coordinate system, then there are some identities we have, right? So Cartesian, when you give people two numbers, it's an x and a y. When it's polar, you're giving them an angle and a radius, right? So here's the relationship, and I think all these relationships make perfect sense. First of all, well, these two we just talked about. X is r cosine theta, y is r sine theta. But why is this true? Right here, x squared plus y squared is r squared.
That's a right triangle.
That's a right triangle, right? Pythagorean. X squared plus y squared is r squared. So we have that relationship. We also have this relationship here that if you want to know the angle, then this is how you get the angle. And that's just, again, off the right triangle. I need to make this a little smaller so it all appears. That still not working. If you want to know this angle, tangent of the angle is y over x. So arctangent of the angle would be theta, right? Would give you the actual angle. Did I say arctangent of theta? Sorry, let me start that over. Tangent of theta is y over x. So arctangent of y over x is theta. That's what I meant to say. All right, so these are our identities that we use if we want to go from one coordinate system to the other. And depending on your pre-cal class, you should have spent a little bit of time in pre-cal converting from one coordinate system to the other. So if someone gives you a Cartesian point, you go to polar, and then back, and from polar to Cartesian. Do we need to practice that, or you all feel okay with it? You're okay? We don't need really to do much conversion. Just remember these identities, all right? Because these we'll use. So, remember when we said that a rectangle in Cartesian coordinates, the way we wrote it was, x is between two constants, y is between two constants. Here, x and y is a Cartesian point. My question to you is, what would it look like if I gave you a polar point, an r and a theta? I told you the theta was between two constants and the radius was between two constants. What does that region look like?
A circle. Sort of like
So think of it this way. If I tell you x is between two constants, then again, you're allowed to move this way and this way a certain distance, right? But your y is between two constants, you can move this way and this way a certain distance. So that draws your rectangle. But now if I'm telling you your theta is between two constants, so maybe like there, and then your radius is between two constants like that. So it would look like this. So let's say your radius, let's do our theta. Okay, if my angle is between two constants, right now it looks like it's between 0 and something, right? But it doesn't have to be 0. It could be maybe between pi over 4 and pi, like that. Yes? I didn't quite get it, but you get the idea, right? That's theta between pi over 4 and pi. Now what if my radius, right now my radius is between like 0 and something, right? But it doesn't have to be 0, it could be like that. You see that? This is what we call a polar rectangle. It's a rectangle in polar coordinates because what's happening here is your theta is between two constants. What am I using, alpha and beta? Hold on. Alpha, beta? Yeah, alpha, beta. So theta is between two constants, alpha and beta. So those are constants. And then my radius is between two constants, and we're just going to use a and b. Do y'all see that? This is a polar rectangle. It doesn't look anything like a Cartesian rectangle, does it? What's nice, though, is this. Let's say that I have, that's the ground, and above that I have a surface. And I want to know the volume from the surface down just over this. You can't do it with type 1 and type 2, can you? Look at, if I draw a type 1, then yeah, you could say that top curve and bottom curve don't change, right? But until you get to here, and then what? the top curve and bottom curve change, don't they? And then when you get over here, they change again. So you could maybe break this down into like several type 1 regions, couldn't you? And then I go and I blow the doors completely off of that, and I do that. And then you can't do it because now it's not even a function of x, right? Like you can't get away with it because your vertical rectangles will be here and here simultaneously. So then you have to somehow break it up even. It's just disastrous, isn't it? So polar regions, this is called a polar region. A polar region is another type of region we want to be able to integrate over, all right? So let's revisit something from Cartesian. Remember when we were setting up the double integral in Cartesian? And we said double integral over a rectangle of the function of x and y with respect to area. And remember this dA came from the idea of this little infinitesimal patch where it was like dx times dy, that's dA, right? That's what we had. Now what we want to do is we want to think about this more from a polar perspective. So the things on the ground are no longer little rectangles, right? Like back up here, it's like a rectangular grid, isn't it? A polar grid does not look like a rectangle. A polar grid, this is like graph paper. You know when you have graph paper? Cartesian, it's like vertical lines and horizontal lines. Polar graph paper looks like a bunch of circles with a bunch of straight radii just going out. So little change in theta, right? Little change in radius. So do you see that little patch right there, that little dA is what we used to have here, right? This is like dx times dy. But how are you going to find the area of that little thing? Because what we're trying to do is figure out how this new formula will look. We're still trying to integrate over a polar rectangle. My function is no longer a function of x and y. It's now a function of r and theta because I've switched to polar. But my dA is no longer dy times dx. It has to do with theta and r. So check out this little picture. d theta means a little change in angle, right? d theta changes here. dr is this change. So this distance from here to here is exactly dr. If you change your radius a little bit, this goes from here to here, right? But if you change your angle a little bit, this piece right here is that we want to know what that length is. How long is this? It's not d theta, right? It's not d theta. It's this. It's r d theta. Where the heck is that coming from? Why is that r d theta? Do you remember this from pre-cal? If somebody gives you a circle and they give you that this is r, and you want to know this thing we called an arc length, s, and if this is theta, that s is r theta. Do you remember that from pre-cal? It's been a long time. But somebody gives you an angle and a radius, you can find how long the outer edge of the pizza crust is by just multiplying the radius times the angle. Now, it was very important in pre-cal that this angle be in radians when you do this. This must be in radians for this formula to work. So do you see where I'm getting this r d theta from? What's the distance from here to here? R, right? That's r. And then what's the angle? Well, it's how much theta changes by. So that's d theta. So if this is d theta, that's really like theta here. And then that's r, so you multiply the two and you get that length. You following me? Y'all are all kind of like... So imagine this infinitesimally small. Just imagine that this d theta is getting infinitesimal, dr is getting this infinitesimal. Then would you agree that this picture, even though it is not a rectangle, this is not a rectangle, right? But because it would become infinitely small, we could approximate it with a rectangle. So if we take this side times this side, dr times r d theta, multiply those two together, we will get an approximation for the red part. And then the smaller d theta gets and the smaller dr gets, the better our approximation will be. But we're going to cut this into an infinite number of pieces, just like we did with our double integral up here, right? dx got really small, dy got really small. More cuts. And so eventually with the limit, we'll be able to make it work. So what do you need to know after all that? Here's what you need to know. That's just me trying to visually explain what the hell is about to happen, all right? All right, so let's say that you have a double integral and your region that you're integrating over is a polar region. A polar region. Then what you're going to have to do is convert your Cartesian double integral over to a polar double integral. Now, your rectangle is going to be a polar rectangle. So it's going to be your radius on the outside with your limits of your restrictions on the radius are between two constants. So you see the a and b go with r, and then your alpha and beta go with theta. But then I have highlighted here that r. Where did that r come from? Why is it? Yeah, that's the formula I was just trying to convince you of. That look, when we do dA in Cartesian, it's just dx dy. But when we convert to polar and we try and get this area, we get this damn little r that pops in here. It's not just going to be dr d theta. It's going to be r dr d theta. Okay? And that means that our formula, every time you go from Cartesian to polar, every time, you must introduce an r into the integral. You have to force an r into the integral. It's not there to begin with. It will be there after you convert. Now, this piece right here, do y'all see that this is f of x times f of y? Do y'all see that? Why is x becoming r cosine theta? That's how you convert from Cartesian to polar. Why is y becoming this? Well, that's how you convert from Cartesian to polar. So that's the Big Daddy formula right there. I think we should do an example so you can see how this is all going to play out. Find the volume underneath z equals 3x plus 4y squared on the region bounded by x squared plus y squared equals 1, x squared plus y squared equals 4, with y being greater than 0. Let's try and get our heads around what the domain is. First of all, do y'all see right here that this is our surface? This is our top surface. So this right here, f of x, y, is equal to 3x plus 4y squared. We're trying to find the volume underneath that, down to the ground, right? But the region we're integrating over is this. This is what? Three-dimensionally, this is what? A cylinder, right, with radius 1, and it comes, goes straight up and down, right? On the ground, it's just a circle. So we have a circle of radius 1, right? And then this one is a circle of radius 2, another cylinder, right? But where it crosses through the ground, looks like this. 2, right? This is our region of integration. We're saying just look above this, right? It's like a washer.
Also,
look at that up to the surface and find the volume. What's that?
Also, doesn't y have to be greater than equal to 0?
I haven't put that in there yet. Yes, y has to be greater than or equal to 0. So that's actually just cut the bottom side off, right? Cut that bottom off. So we're actually just looking at that piece right there. Right? Now, do you want to go after that as a type 1 or type 2 Cartesian? No way. You don't want to mess with it, okay? This is a perfect polar rectangle, isn't it? Okay, so if it's a polar rectangle, this is a polar region. As a polar region, you need to tell me the restrictions on theta and r. Those are the things that are important here. So can you tell me for that region what my restrictions on theta are and what my restrictions on r are? 0 to pi and 1 to 2. So simple to define this region in polar coordinates, right? 0 to pi, 1 to 2, and we're done. But now what we need to do is we need to convert over our function. This right here has to be converted to a function of r and theta. You all okay?
Yeah.
Okay, so I'm going to set up a double integral. Let's put the limits of integration on at the end. I'll just wait for now. I want to rewrite this, but everywhere I see x, I replace it with what? R cosine theta, and everywhere I see y, I replace it with r sine theta. That's all I do. So I do 3 r cosine theta plus 4, what? R squared sine squared theta. So I have to square the r and the sine, right? That make sense? Okay, that's the function replacing x and y with their respective polar conversions. Now what? R. Okay, this is where you have to put the r in. Right here, times r, highlight, right? Somebody's going to forget that. And if you forget it, it's all wrong, okay? You've got to have an r in here. Now, d theta dr or dr d theta? What do you think? Or does it matter? Look at your limits of integration. They're constants. Okay, so it doesn't matter. You just have to match them up correctly. All right? So I can either go dr d theta or d theta dr. What do you want? D theta dr? Okay, that's fine with me. All right, if I do it that way, then r's on the outside. So 1 to 2 here, and then 0 to pi here. So now this becomes integral 1 to 2, integral 0 to pi, 3r squared cosine theta plus 4r cubed sine squared theta d theta dr. And that's it right there. Are there questions on the setup? Anyone have any questions on where we got like the picture over here from up there or anything? If you had to integrate that with respect to theta, then we'd be treating this like a constant, right? So the antiderivative of that would just be sine theta, we'd be happy, right? This would be a constant. The antiderivative of sine squared. Well, then you got to go back to Cal 2. Whenever we had sine squared, we'd use the power reducing formula, and we would turn sine squared into 1/2 cosine. You remember this? Cosine theta minus 1 or something like that. What's that? Cosine 2 theta, right? Hold on, I'm having a brain fart. I'm having a complete brain fart. Wow, I don't forget formulas like this. This is not something I normally do. I just don't know if that's 2 theta or not. Just give me a second. Let me go get a drink of water. Don't tell me. I don't want to know. No, because when you reduce the power, it's give and take. You have to double the angle. You don't get nothing for free. I'll be right back. Right? 2 theta? Where is it?
Yeah, it is.
I have it backwards? That's why I'm freaking out. Okay, that's why. I haven't used this formula in a while, I guess. 1 minus cosine 2 theta. Okay, there we go. Yeah, I feel like a rookie right now. When I get to math, the judgment day, math judgment day, all my mistakes, I'm gonna be punished for. All right, there we go. Does that look more like it? Okay, so you do that, then you'd have to, then you could integrate these piece by piece. Antiderivative of 1 would be theta, and then this would be, you have some constant you have to deal with, and then, yeah, this, I'm not going to continue because time, okay? But you need to be able to do this integral. So I would maybe take this one and finish it off on your own. One last thing I want to show you in 5 minutes. I think this is pretty mind-blowing, what I'm about to show you right here. You may not agree, but you can share this with your friends. Prove that the area of a circle is pi r squared. Okay? I want to prove that the area of a circle is pi r squared. You ready? I've got to go fast because I only have 4 minutes. Okay, if I have a circle of radius r, I want to prove that the area is pi r squared. The way I'm going to do this is using this idea. Remember I told you put this on the back burner? Right? Remember I told you put that on the back burner? If you do a double integral over the surface constant 1 over d with respect to area, that this is the area of d. Okay? So I'm going to imagine that this is my d. This is my d down here, okay? And above it is a surface that's 1 unit high. Right? Like that. There's d on the ground. This is 1 unit. I'm going to find the volume of that. But I'm going to go to polar coordinates because this is a polar region, isn't it? So theta would be between where and where here? Careful. 0 to 2 pi. Okay, what would r be between? And here I'm going to run into a little bit of a problem. R is between 0. No, because the polar region, I start here, right? Go here to here, and then I rotate it around 2 pi. So 0 to what? R, but I can't use little r again. So let's change this to capital R, change that to capital R, and change that to capital R. Do you all understand what I'm doing here? I just can't use little r twice because one of them is a variable, one of them is a constant. Got that?
Yes, sir.
Okay, now, check this out. Double integral, I'm integrating what function? 1, right? But I'm going to polar from Cartesian. So what does dA become in polar? R, right? R. And then it doesn't matter dr, d theta, dr, doesn't matter? I'll do dr, d theta this time. And that means I go, theta's on the outside, 0 to pi. And then here, 0 to capital R, right? You ready? Let's do the inner integral. I'm going to do this in plenty of time. 0 to 2 pi. The inner integral. What's the antiderivative of r with respect to r? 1/2 r squared. And I'm going to evaluate that from where? From little r equals 0 to little r equals capital R. And then when I'm done with that, I'm integrating with respect to theta. So plug capital R in, and what do you get? You get integral 0 to 2 pi. You get half of big R squared, right? And then you plug 0 in, and it's gone. And then you're going to integrate that with respect to theta. What's the antiderivative of this with respect to theta? Well, that's all a constant now, isn't it?
Oh, yeah.
Right? So this is just 1/2 capital R squared times theta, evaluating theta from where? 0 to 2 pi. So replace theta with 2 pi first, and what would happen?
The
Twos cancel, and you get pi r squared. And you place theta with 0, and you get 0. And there it is. I went fast. Did y'all follow that or no?
Yeah.
I mean, you can look at, with polar coordinates, you can prove the area of a circle is pi r squared in less than 3 minutes. And you can do the same thing. We're going to do it later. We'll prove that the area of a sphere, the volume of a sphere is something, and we can do a lot of really hard formulas with polar and spherical coordinates. All right, that's 2:40, you have a take-home exam. Don't forget, you also should be keeping up with your homework here. Have a good day.
So I went back through.
Okay.